Section 3.3, Systems of Linear Equations. Okay, what are we talking about when we say a system of equations? Well, we're talking about something that looks like this, where you have more than one equation, and we're kind of looking to see how they interact with each other. And what I mean by that is, there's an ordered pair, right? Possibly an ordered pair, an x and a y value that would work for that first equation, right? There's a bunch of them, actually. And there's another several, or an infinite number of ordered pairs that work for this equation. Do they have a point where they share an ordered pair? Okay. In other words, if I graph these, do they intersect each other somewhere, right? That's what we're looking for. And so there's a variety of methods to figure that out. But what we're going to do here is, well, I'm just going to use two different methods, and you can watch the individual help videos if you want to see them broken down a little bit more. But for now, what we'll do is I'll just pick methods as I go. So this 2x plus 2y equals 6, and this 5x plus y equals negative 1. This one's set up pretty well to use what they call the elimination method. Elimination. Or maybe even the addition method is what it's called sometimes. And so that's what I'll do here. So 2x plus 2y equals 6. I want to alter this second equation in such a way that if I combined the like terms vertically, something will cancel out. Okay, one of the variables will cancel out. In this case, it's easier to change the bottom equation such that this positive y right here becomes a negative 2y. Okay, so how does that work? I'm going to multiply this bottom equation times negative 2. Okay, so multiply that times negative 2. Every single term there. Negative 2 times 5x is going to be negative 10x. Negative 2 times y is negative 2y. Negative 2 times negative 1 is going to be positive 2. Okay, so notice what we've done is altered that equation. The graph of that equation is the same. Okay, so let's keep that in mind. The graph is going to be the same. The only thing that's changed here is the way that we have that equation written out. It's like changing between standard form and slope-intercept form. You change the form, you still have the same equation, at least as far as ordered pairs. Okay, so let's now add these two together. Okay, well, 2x minus 10x would be negative 8x. Right? And I said minus because you're adding a negative, right? Okay, and then 2y minus 2y, those actually cancel each other out. Bring down the equal signs. 6 plus 2 is 8. So you'll notice I added the two equations together in such a way that a variable was eliminated, right? That's the names, elimination method or the addition method, okay? So let's keep going. Negative 8x equals 8 is a simple equation. To solve that, divide both sides by negative 8. 8 divided by negative 8 is negative 1. Okay, so we have an x value. Remember, we're looking for a shared ordered pair, a shared point. So we need to find a y value. Well, just take this negative 1 and substitute it in to either one of those equations. Okay, I'm going to go with let's go with the top one. 2x plus 2y equals 6. So 2x plus 2y equals 6. And we have decided that x, at least the x value that we're interested in, is negative 1. So I'll plug in negative 1. 2 times negative 1 plus 2y equals 6. Okay, well, 2 times negative 1 is negative 2. So negative 2 plus 2y is equal to 6. Let's add 2 to both sides. Those will cancel. 2y equals 8. Divide both sides by 2. And I get a y value. Y equals 4. So it turns out that negative 1 comma 4 is an ordered pair that works for both of those equations. Okay, and so you can actually visualize that. If you were to graph those two equations, you would see this right here. Okay, the red one represents the top one and the blue one represents the bottom one. Okay, notice they intersect each other at a particular point. Where is that point located? Negative 1, comma, 1, 2, 3, 4. Okay, so that's what we're looking for. Now, they're not all that straightforward. So here's another one. Let's do another one. Y equals 1/2 x plus 4, and 2x minus 4y equals negative 16. Now this one's set up nicely for us to use the substitution method. That's my favorite method right there. I like this one the best because it works for more scenarios, okay, most scenarios. So it's called the substitution method because if you look at them carefully, yes, you still have two equations, but since this one has y set equal by itself, right, y is equal to something, I can read that as saying y is the same thing as 1/2 x plus 4. Y is the same thing as 1/2 x plus 4. If that's the case, then this equation 2x minus 4y equals negative 16, I can rewrite that one as 2x minus 4 times y equals negative 16. Notice I left a blank where y was. That's because we just said y is the same thing as 1/2 x plus 4. Right? That's what that equation is telling me. So, why is that useful? Well, because instead of having two equations with two variables each, I have one equation with only one variable, right? One equation with an x. I can solve that like I solve all my other equations. Okay? We know we need to distribute the negative 4. So let's bring down the 2x. We'll distribute negative 4. Negative 4 times 1/2. Half of negative 4 is negative 2. So negative 2x. Negative 4 times 4 is negative 16. And then we'll bring down the rest. Equals negative 16. Okay, so now we have three terms on the left. We need to combine like terms. I see that I have 2x and negative 2x. 2x minus 2x is 0x. Oh, they canceled each other out. Okay, we have a special case here. Something is happening. Negative 16 equals negative 16. What do I do with that? Okay, well, let's investigate a little bit further. Let's look at these two equations separately. Okay, so y equals 1/2 x plus 4, 2x minus 4y equals negative 16. Let's put them in the same form and see what we get. I'm going to convert this one to slope-intercept form. Okay, I think that's the easiest thing to do. So remember, to put that in slope-intercept form, we need to get rid of the x variable term first. That's on the left side. So I'll subtract 2x from both sides. I'm trying to get y by itself, right? So negative 4y equals negative 2x minus 16. Now let's divide everything by negative 4. Divide everything by negative 4. Well, those will cancel, leave me with y equals negative 2 over negative 4 is positive 1/2. And then negative 16 divided by negative 4 is a positive 4. Oh, so that's why this one gave us a weird solution, right? Negative 16 equals negative 16, which is true, by the way, right? Negative 16 does equal negative 16. It's because these are the same line. So if you are given the same line twice, you will end up with a true statement like negative 16 equals negative 16. If that happens, you have a same line. That means that they share all the same points, right? Think about it. If these two are the exact same line, the same graph, of course, whatever points work for this one, whatever ordered pairs work for that one, also will work for this one. They're the same, right? So you could say that there's an infinite number of solutions. Infinitely many solutions. And that's actually the standard answer to this question. If you tried to find the solution to the system of equations, their intersecting point, you would find that there's an infinite number of them. Okay, let's actually look at the graph real quick. If you were to graph the two, again, you have the exact same thing twice. You have the same line on top of each other. And so that's why I went and put a little point on all of these to show that they intersect everywhere, even at the little points that I don't have listed. Everywhere they're intersecting. Okay, let's do another one. 2x minus 5y equals negative 5. Y equals 2/5 x minus 3. Okay, here's another solution that looks set up well to do, or another system that's set up well to do substitution. Okay, y is by itself. So anytime you have a variable by itself, substitution is usually a pretty good idea. All right, so I'm going to exchange this y for the thing that y is equal to, which is 2 fifths x minus 3. So let me rewrite this. 2x minus 5 times y equals negative 5. And the y in question here is the same thing as 2 fifths x minus 3. 2 fifths x minus 3. Okay, let's bring down the 2x. Let's distribute the negative 5. Negative 5 times 2 fifths x is going to be negative 2x. Right, the 5s would cancel. Negative 5 times negative 3 is a positive 15. Let's bring down the equals negative 5. Okay, again, we have 3 terms on the left side, so let's go ahead and combine our like terms. Oh, here we go again. 2x minus 2x canceled out. We have another special case, back to back. So the last one we had a true statement, right? Negative 16 equals negative 16. In this case, we have a false statement, right? That is not true. 15 does not equal negative 5. So how do we make sense of that? Well, let's go ahead and again rearrange these equations, put them in the same form, and see if we could figure something out. Okay, I'm going to put this one in slope-intercept form. I'm going to subtract 2x from both sides. Keep in mind, these are not like terms, right? So I can't put them together. By now, I think you got that. Negative 2x minus 5. Then I'm going to divide everything by negative 5. Okay, so that's going to give me y equals negative over negative is positive, 2 fifths x, negative over negative is positive, so positive 1 plus 1. Compare that to this one. Okay, maybe you're seeing it right there, right? The number attached to the x is the slope. They have the same slope, but their y-intercepts are different. So what does that mean, right? Well, kind of think about what that's saying. The steepness, right, the slope is the same, but their starting point, the y-intercept, is different. Okay, can we visualize what's going on there? These are two parallel lines. They never intersect each other. They don't share a point. It's impossible for them to share a point. So you would say then, if we go back up here, if this were to occur, there's no solution, because you're dealing with parallel lines, lines that never intersect each other. No solution. Okay. Let's keep going. All right. This is a problem that looks better set up for the elimination method, so we'll do that one. 5x minus 4y equals negative 12. 4x plus 5y equals negative 26. Okay, again, I want to figure out a way to cancel them out, either the x's or the y's. I have to just pick whichever one I want to cancel out. Now, I think it would be easier to get rid of the y because I have a negative and a positive, and you know if you add a negative and a positive, you're basically subtracting them, right? And so if I can just get these to be the same number, then they'll cancel out. So that's the trick. I'm going to look to multiply the top and the bottom by different numbers to see if I can get a positive and a negative of the same value, okay? Think about common multiples, right? What could I multiply, or what could I do, what could I change this into and this into so they'll cancel out? I'm going to change it into a negative 20 and a positive 20. A negative 20 and a positive 20. To do that, I'm going to multiply the top one by 5. And I'm going to multiply the bottom one times 4. Okay, so let's do that. Multiply the top by 5. 5x times 5 is 25x. Negative 4y times 5 is negative 20y. And negative 12 times 5 is going to be negative 60. On the bottom, 4x times 4 is 16x. 5y times 4 is 20y equals negative 26 times 4 is negative 104. we go. So now they're set up. The numbers are bigger, but it's going to work out nice. Add them. 25x plus 16x is 41x. Negative 20y plus 20y is 0. They cancel each other out. Bring down the equal sign. Negative 60 minus 104 is negative 164. So 41x equals negative 164. Divide both sides by 41. X equals negative 4. X equals negative 4. Okay, so to find the y value now, let's go back and plug negative 4 into one of these equations. I'm going to go with the top one. I don't know why, that's just the one I want to use. So 5x minus 4y equals negative 12. I'm going to substitute negative 4 in place of x. 5 times negative 4 is negative 20. Minus 4y equals negative 12. I'm going to add 20 to both sides. Those will cancel. Negative 4y equals 8. Negative 12, negative 12 plus 20 is 8. Divide both sides by negative 4. Y equals negative 2. Okay, so I got an answer, negative 4 comma negative 2. That's the point that both equations share. Okay, but the reason why I'm doing this one has the last problem that I want to do is because there's actually something special going on with this one. It's another special case, even though it doesn't quite appear so. Okay, so let's go ahead and look at their graphs, and then we'll go from there. Look at how they're intersecting each other. Maybe it's hard to see it, but they're actually intersecting at a 90-degree angle. Okay? They are intersecting perfectly, okay? And so these are perpendicular lines. I don't want to just stop right there, though. Let's go and see if we can figure out a way that we can tell two equations are perpendicular lines. Okay? So let's rearrange both of them, get them in slope-intercept form, and see what we find out. So subtract 5x from both sides. Negative 4y equals negative 5x minus 12. Divide by negative 4, all terms by negative 4. Y equals negative over negative is positive. 5 over 4x. Negative 12 over negative 4 is a positive 3. Okay, let's rearrange 4x plus 5y equals negative 26. Let's subtract 4x from both sides. Those will cancel. 5y equals negative 4x minus 26. Divide by 5. All three terms divided by 5. Y equals negative 4 over 5x minus 26 over 5. Okay, maybe nothing is jumping out at you right away, but look at the slopes a little bit more closely. We have 5 over 4, we have 4 over 5. They are reciprocals of each other. We have a positive, we have a negative. They're opposite signs. Okay, together they make up perpendicular lines. Okay, these lines are perpendicular. Their slopes, well, I'm not write this down because I already typed this up. They have slopes that are opposite signs, and they are reciprocals of each other. So therefore they intersect at a 90-degree angle. That's how you can tell that they are perpendicular lines. And again, in summary, here's all our special cases. Most systems of equations will not be one of these three, right? These are just three special cases. So either you have parallel lines, that means they have the same slope but different y-intercepts. They never intersect each other. There's no solution if you're trying to solve it. Perpendicular lines have opposite signs. Their slopes have opposite signs. The slopes are reciprocals. They have a solution. They just happen to be at a 90-degree angle. They intersect at a 90-degree angle. Okay, and then last, same line. They share the same graph, right? If it's the same line, they have the same graph, right? The slope and the y-intercept are identical. So therefore you have an infinite number of solutions because they intersect everywhere. Okay, and there are some other things that we need to look into, so special cases, and I encourage you to look at the individual, the little example videos that are posted to see all the other little special cases and a more in-depth breakdown of the addition method or the elimination method and the substitution method. But that basically summarizes everything in section 3.3. So that would be the end of this section.